Thanks for joining in, everybody. So thanks for tuning in here. This should wrap up our 7 packets. This is a fairly quick one. The packet, probably like I mentioned in class, really is just some minor things. Wouldn't be huge parts of the test, but certainly things that you were responsible for and would possibly see, just not something that you're going to see too much of. So first, this first page really is just dealing with sketching some curves. Definitely some vertical, horizontal asymptote questions would probably appear, and that's kind of what we start with here. So the first one is just if I had to have you sketch this curve. What we did with these first was identified if we had any asymptotes. In this case we do. You have 2 excluded values here that we can never get rid of. Whenever you have excluded values, that means you have vertical asymptotes. So for this graph, your excluded values are 2 and -2. So that means on our graph, so if we were to draw this on a graph, since I'm wandering over to here, make a little XY plane, we would know at -2 and +2, we have vertical asymptote. In terms of how we write those, in terms of an answer, these are lines, vertical lines. So your vertical asymptotes you would always write as such. Vertical lines are x equals some constant. In this case, it's a plus or minus 2. And then we would have them in our graph. All right, so that's our first step. Next, to figure out your horizontal asymptotes. What a horizontal asymptote basically asks is, as we move further and further and further left on our graph, and further and further and further right on our graph, what y value would we approach? So what we're basically doing is we're taking this function here and we're calculating its limit as x goes to infinity. I'm going to switch to a pencil so I can erase some of this. So we're going to take this function and we're going to find this limit as x goes to infinity. It's one of our infinity rules, things that are pretty simple. Here your bigger degree is on the bottom, so your limit would be a 0. So that means we have a horizontal asymptote at y equals 0. So over here, the x-axis is acting as a horizontal asymptote. All right. So that's our asymptotes. You're certainly going to see something on that. If we had to continue this and finish graphing this, the next thing we would try and find were the x-intercepts and your y-intercepts. So if we went and found these, or tried to find these, to find our x-intercepts, you would let your y be a 0. Well, if I let y be a 0 here and tried to solve this, I would end up with 0 equal to 8 over x squared minus a 4. If I multiplied that over, it would cancel here, and when I multiply on the other side, I would just end up with the equation 0 equals to 8. That's obviously not true. So what that means is there is no x-intercept. All right, so you would just say none. Y-intercepts, the opposite. You would let your x be a 0. If x is 0, you'll get a -8 over -2, so our y-intercept is 2. So what that means is on our graph, we'd come on over to the y-axis at the value of 2. We know we're crossing the y-axis. From there, it was all the stuff that we were concerned about. This is when we did our increasing, decreasing, max bends, all that. So we needed to figure out our critical points. Critical points are when your first derivative is either 0 or undefined. So we need our first derivative. It's a quotient. So we'll do the quotient rule. You're going to do your denominator. The derivative of your top, the derivative of a -8, should be 0. And then you would subtract the numerator, which is a -8. And your denominator's derivative is 2x. All that gets divided by your denominator squared. So next thing, we'll clean it up. As we're cleaning it up, to get our critical points, we're going to look to see where does this equal 0. So those would cancel, giving you a 0. Then we get a positive 16x over x squared minus 4, quantity squared. So in terms of testing numbers on our number line, for sure, we're testing +2 and -2 because that's going to make our derivative undefined. So -2, +2 must be tested for maxes and mins. Use those to figure out where we're increasing and decreasing. However, we also want to try and solve this for x. What that means is if I multiply my denominator over, it's going to cancel here. I'll get a 0 on the other side. What we're left with, though, in this case, I don't know if you can see this. Move over a little bit. If we multiply this over, you're going to end up with 0 equals 16x. That you can solve and get the x value of 0. So 0 is also a test point. All right, those are our 3 test points. We get the -2 because it makes our derivative undefined. We get 0 because it made our derivative equal 0. So we will then test these. So we want to figure out where are we increasing, decreasing, all that. -3. Well, let's go to our derivative to make this easy. Your denominator will always get squared. So no matter what I plug into my denominator, I'm going to square it and it's going to become positive. So really it just matters what's going to happen to my numerator. So if I take a -3 and plug it into my numerator, it's going to be negative. If I take a -1, plug it into my numerator, it's going to be negative. On the other side of 0, you're going to get +1 plugged in, it's going to be positive. +3 plugged in, also positive. So what we know we have is at x equals 0, you have a minimum. When we curve sketch, when we actually draw the graph, we don't just want to know your x coordinate, because we're going to have to plot the point. We would also need to know our y coordinate. Well, if you know x is 0, you'd come up here, plug it in to figure out what y is, and what you'll see is y equals a 2. That just so happens to be our y-intercept that we had graphed earlier. So this is going to be a minimum. This should be a low point on your graph. Okay. Pretty much at this point, we can graph this. Just understanding asymptotes and our sign chart, we can graph this because what has to happen is for an asymptote to exist at 0, which we say we have a horizontal asymptote at 0, our graph has to level off towards 0, either from the top or from the bottom, one or the other. If we know we're decreasing to the left of -2, so here's -2 on our graph, here's the -2 on our sign chart, we know our derivative is negative, we have to be decreasing all the time. We would have to then conclude that we are down here. We're always decreasing, decreasing, decreasing. And as we approach this vertical asymptote, you can't cross a vertical asymptote, so you're slowly but surely going to just shoot straight downwards. And our graph over here would have to look like that. All right, so we level out towards that asymptote, decrease the whole time. And then as we approach the vertical, we have to shoot straight down. Over here, same idea. As we go further and further right, if our horizontal asymptote is 0, that means we are either leveling off towards 0 here, or we are leveling off towards 0 from the bottom. If we look at what our graph should be doing, here our derivative to the right of 2, so here's 2 to the right, 2 to the right, the derivative is positive. If the derivative is positive, our graph has to be increasing the whole time. Well, the only one that's increasing of these two is this one. This is the one that's going up. So our graph would have had to have been doing this, increasing the whole time. We can't cross this vertical and eventually leveling off towards that asymptote. All right, in between a -2 and a +2, if you look around 0, so in between -2 and +2, that's where we should have had a minimum. Okay, hopefully you can see that it's a minus positive. So that means we decrease in between -2 and 0. So here's -2 and 0. We're decreasing this whole time. Between 0 and 2, we start to increase. So here's 0, here's 2. We should increase the rest of the way, and we can't cross these vertical asymptotes. So we would just be running up alongside of them. This would be our graph. All right. All right. The next couple, we want to be able to do this. In terms of it being on the test or not, may or may not. What would almost certainly be on there, though, is the asymptote part of it. So 2 and 3 are just finding our asymptotes. The vertical asymptote should be the easy one. You're going to look at your function and just determine what's undefined. In this case, x can't be 5, so your vertical asymptote would be x equals 5. Write it as an equation, vertical line. This eraser is really bad. All right, for your horizontal asymptote, you're going to take your function, and we're going to look to see see here. You're going to take your function that I'm giving you, and we want to find the limit of this as x goes to infinity. These have the same degree, 1, 1. We look at their coefficients, 1, 1. So your limit is a 1, so that means your horizontal asymptote is 1. Okay. Second one, x squared minus 25. Your excluded values here are positive and negative 5, so our vertical asymptotes are positive, negative 5. Horizontal asymptote we find by taking the limit of our function as x approaches infinity. So this function, you have a degree of 1 on top, a degree of 2 on the bottom. The bigger degree is on the bottom, which means your limit would give you 0. So that means our horizontal asymptote is y equals 0. And that's it. So that's our quick little review of asymptotes. Skip 4 real quick. Go down to 3. Skip 3 real quick and go down to number 4. Oops, wrong way. Number 4 says y equals 7 is a horizontal asymptote. 1, this is a horizontal line equation. Y equals some constant. You are told it's a horizontal asymptote. Then it's asking, then which of the following must be true? Well, anytime you see horizontal asymptote, the way we find a horizontal asymptote is by taking the limit of whatever the function is and seeing what happens as we go to infinity, or really negative infinity. It could be positive or negative infinity. We just want to know, like up here, what happens as we go further left, what happens as we go further right. So that's why we could be finding the limit of positive or negative infinity. So when you look at your choices, once you know you have a horizontal asymptote here, that means we found a limit as x either goes to infinity, or we found a limit as x goes to a negative infinity, meaning it can't be a, d, or e, because these are calculating limits as we go to 7, 0, and 7. Horizontal asymptotes, we have to be approaching infinity or negative infinity. When we did it up here, whatever our limit was, in this case it was 0, that was your horizontal asymptote. This is just backwards. I'm telling you your horizontal asymptote is 7. So that means the answer to this limit problem better be 7. This is the one that gives you the 7. This had a negative 7, which means this is the one that we're looking for. That's the one that must be true. Limit as x goes to infinity for your function is always how we find a horizontal asymptote. Okay? All right, that's the little review on asymptotes. Next thing, last curve I want you to graph. There are no asymptotes here. There is no excluded value in your denominator, so we don't have to worry about that part of these problems that we just did. No asymptotes. But we do want to be able to sketch this. So since there are no asymptotes, the first thing you're just going to do is find your x-intercept and your y-intercepts. X-intercept, you're going to let your y be a 0. So if y is a 0, you would get 0 equals 3 plus the cubed root of x. Subtract that over, negative 3 equals cubed root of x. Cube both sides, x would equal a negative 27. The y-intercept is easy. You would let x be a 0. If x is a 0, you just end up with y equals 3. Okay? So, with regards to our graph now, somewhere over here, go ahead and start to draw your graph in. What we found is our y-intercept was a 3. Our x-intercept is way over here at a negative 27. All right? So, x-intercept, we have to cross this point. Y-intercept means we have to cross that point. All right, we got that at the beginning. Next thing, we want to figure out our critical point. So you're going to take your derivative. Derivative of y would be 0 for the 3, and then here, careful with your fractions, you'll get 1/3 x to a negative 2/3. In order to figure out some points to test in our derivative, you're going to set this equal to 0. As you're setting it equal to 0, you're going to want to simplify this. So we have our 1/3, all right, from here, so 1/3. X was raised to a negative power, so we'd put that into our denominator. It becomes a positive 2/3 down here, and then a 2/3 power means a cubed root of x squared. All right. So in terms of testing, let me clear some space here. In terms of testing our values, Not only are we worried about where your derivative equals 0, we are also concerned about where our derivative is undefined. Well, if this is our derivative, the x value that would make this undefined is 0. 0 must be a test point. We would still need to try to solve this equation. To do that, you would multiply the cubed root of x squared over. That would cancel. But when I multiply by the cubed root of x squared over here, I'm just going to get 0 equals 1/3. That obviously isn't true, which means there is no other point to test. There's no place on this graph where your slope is 0. Okay, so let me get rid of that. So the only test point is the test point that made our derivative undefined. And what made our derivative undefined here is a 0, so we're testing that. Your sign should be pretty simple. Your numerator is a positive 1. Your denominator is a positive 3. No matter what x value you're going to plug in, you're going to get a positive number because you're going to square it. So basically everything is positive. So left and right of 0, we are positive. If our first derivative is always positive, that means our graph has to always be increasing. So that's a bare minimum. We have to always be going up. Okay? That's what we can figure out from that. We don't want to use this just yet because we want to figure out our concavity. Are we concave down, concave up, concave down? You know, what kind of concavity do we have in here? What's the shape of the graph? So the next thing we need is our second derivative. So I would use this one. So now over here, let's do our second derivative. So now you're going to take a negative 2/3 times a 1/3. So that's a negative 2/9 x to the, subtract 1 from the negative 2/3, should be a negative 5/3. Our test points we would get by trying to set it equal to 0 and solving. So you'll get your negative 2/9. Put the x into your denominator because of the negative power, and it would be a cubed root of x to the 5th power. Well, 0 makes the second derivative undefined. So we've talked about earlier in some of these packets, we can get points of inflection when the second derivative is undefined, not just when it equals 0. So we have to test 0. If we tried to solve this equation again for x, so if we multiplied this over, it would cancel. When you multiply on this side, you're going to get 0. So you would end up getting like 0 equals a negative 2/9. That's not true. So there is no other point to test. We are only worried about 0. To test it, look at your numerator. It's always negative. It's a negative 2. So if I now take a negative 1, I'm going to raise negative 1 to the 5th power. That's a negative. The cubed root of a negative 1 is negative, and then a negative 1 times 9 would be a negative 9. So I'm going to get a negative over a negative, which means here we are positive. Positive 1 plugged in, your numerator is negative. If x is a positive 1, then your denominator would be positive. So you'd have a negative over a positive, which is negative. So what that means is, as we increase the whole time, which is kind of what we roughly sketched in before, you also have to change from concave up to concave down. So what this would then look like, initially it's going to look like this. We're increasing as best we can concave up. It's kind of a small graph. Then you're going to continue to increase but be concave down. So we continue to increase but you're going to be concave down. And then here's the big thing about this. Notice how our derivative was undefined at 0. There's only 3 things that make your derivative undefined. A sharp corner, a vertical tangent, or, try making that a D. Vertical, no, what am I doing? Vertical tangents, and a discontinuity. Well, there is no discontinuity because at x equals 0 we get a value. If I plug in 0, I'm going to get a 3. So at 0 you either have a sharp corner or a vertical tangent, and if you just kind of look at the way this is formed, what happens is this thing just goes vertical at this one moment as we change from concave up to concave down. So you would need to somehow show that your graph goes vertical there. All right? Okay, it's a pretty bad graph, but bear with me. All right, next page. I'll make this easy for you. Length of a curve is not an A-B topic. So what that means is you can take this and cross this out, you can take this and cross that out. All right, so basically don't worry about 5 and 6. Don't worry about the length of a curve formula. All right, not a A-B topic, it's only for BC. All right, last thing on this page then, 2 more things. Last thing was your growth and decay. The thing you're gonna wanna be careful of here, they will likely give you this equation, dy dt equals ky, or they won't give you the equation, they'll put it into words. And this says where the change in some quantity y, so that's why this is the change in y over the change in time. So with respect to time, so change in y over change in time is equal, so it should say equal to, so equals the rate, that's what k stands for, it's your percentage rate or decay, which is decay, times the amount present, so multiplied by however many there are. So they'll either give you this or they're going to give you this little saying, the change in some value, population, is always equal to the rate of growth multiplied by the amount present. Okay? We integrated this when we did it in class. We'd always separate these, so we would like do dy over y. We'd multiply the dt over. So then you would get k dt. We did the antiderivative of these, all that good stuff. What this always produced was the law of exponential growth and decay that you have here. Go this way. Where y of t is your population at any time, y sub 0 is your initial population, what we start with. K is your percent, so if you increase by 2%, 3%, that's your k, and then t is your time. All right, so a problem. We'll do a couple. These are kind of the standard problems with these. It says population y grows according to this differential equation, where k is a constant and t is measured in years. If the population doubles every 10 years, the value of k is what? For us to answer this, you would need to integrate this. We don't want to have to go through all the work to do that. So the integration of this is the exponential growth and decay formula. I'm going to use p's because it's a little more applicable to a population. So our population at any time would equal the initial population multiplied by e to the k t. Okay? You're looking for k, so this should be the variable that we are left with. You were given your time, 10 years. What you weren't given is the initial population or your population in 10 years. You weren't given either one of these. Fairly common. This is when we let the initial population stay the same because we don't know it. But what we do know is going to happen is we're going to double our initial population. So if our initial population is p sub 0 and it takes 10 years to double, then if I let this be a 10, I can say that my population then would be twice the initial. So initial, twice the initial. Now we can go ahead and say these cancel. You're left with a pretty simple little equation to solve here. E equals, or e to the 10k equals 2. To solve for k, we need to get rid of the e. You'd use a natural log to do that. So you do the natural log of 2 equals the natural log of e to the 10k. Those cancel. You get the natural log of 2 equals 10k. Divide by the 10, and you should get 0.069, which is A. All right. 8, it says, a city had a population of 10,000 in 1980, 13,000 in 1990, assuming an exponential growth rate. So this one is telling you that. Estimate the population in 2000. All right, we've done this one. What this is saying is in 1980, we had a population of 10,000 people. In 1990, this city had a population of 13,000 people. And the question was, how many people would we have anticipated in 2000? So what we're going to do, try to answer this question here, is if this is our initial time, and we're looking for our population in 2000, there has been a 20-year lapse here. So our answer to this is going to be, what is our population after 20 years? That's the answer to this question. To do that, you're going to set up one of these exponential growth and decay problems. Since I want p of 20, that means I'm going to go over here and I need to let my time be a 20. All right. Here we're going to say P of 20 equals whatever this is going to give us. Well, you know the initial population as well. That was 1,000. I'm sorry, 10,000. And then 13,000. So 10,000. So our population after 20 years, this is your initial, this is our time, 20 years. You just don't know your K yet. These are fairly common where you got to kind of go back and forth. The information here you're going to need to use, and that information gives us a elapsed time of 10, 1980 to 1990. So what that means is we're going to set up another one, P of t equals P sub 0 e to the kt. If I let my time be 10, then I can say my population at that time, so my population at 10 was 13,000. So then I go ahead and let the left-hand side be 13,000. The initial population at the beginning of that 10 years is still 10,000. And what we now have is a little equation here that you can use to solve for K. We would want to divide by the 10,000, so divide, and it gives you 1.3 equals e to the 10k. Take the natural log of both sides, so you'll get the natural log of 1.3 equals, it cancels out the e, 10k. K equals the natural log of 1.3 divided by 10. Now what we want to do is to take this value of k and plug it in over here. You don't want to round that. You're going to have to use your calculator at this point. There's really no way around that. So the natural log of 1.3 over 10, you probably have to plug that in, which is what I'm currently doing. It should give you this. 0.02623, ... We don't want to round this. Oops. We don't want to round this. You never, ever, ever round until the very final answer. So this is one, when your calculator gives you this, you're going to want to store this. So you're going to want to store this as your x. So do that number, store as x, hit enter, and then now your calculator knows that's your x. And then you would just plug this into your calculator, because this x value is your k. Throw this in, and what we should get is 6,900 people. All right. Last but not least is inverse functions and their derivatives. All right, inverse functions, if you remember, if I have a function and I have the inverse of that function, so this is inverse notation here, the little -1, any point found on f, the inverse, those get flip-flopped. That's why if I ever had you find an inverse, like y equals x cubed plus 2, to find the inverse of this, we would flip-flop the x and the y, and then resolve this for y. And the reason for that is a function and the inverse, inverse basically means it's the opposite. So the x and the y get flipped around. Ooh, yeah. So the x and y get flipped around. So what this is saying now, the value of this, and notice that this is our derivative notation with a little -1. So what this means is this is the derivative of your inverse at any point f of a, so functional value, is the reciprocal of the value of your derivative at a, which is really confusing. So the two different methods we can use to do this. It says find the derivative. This is our derivative notation to a -1, so that means it's the derivative of the inverse using two methods. All right, we're going to do method number 2 first, okay? Method number 2 is actually using inverses and taking their derivative. So what we would do is take this function, y equals x cubed plus a 1, and we want to find the inverse of that. That required us to flip-flop these, resolve this for y. So you would get y cubed equals x minus a 1, take the cube root of both sides. This would then be considered our inverse. So this is the inverse of that original function. Well, what we're trying to do is find the derivative of our inverse. So now that we know this is our inverse, so it's a -1 here, we just need to take the derivative of this thing. So I'll do that over here. Let's first rewrite this. So our inverse would have x minus 1 to a 1/3 power. And we want to take the derivative of that. So the derivative of the inverse of y would equal, we have a little chain rule problem. You're going to have to multiply by 1/3. Leave the inside alone. Subtract 1 from your power to get a negative 2/3. Simplify. So you'll have your 1/3. Negative power, a lot of fraction practice today. Put it into your denominator, and it's a cubed root of x squared in your denominator. So the cubed root of x minus 1 squared. That's your derivative of the inverse. If you go back to the problem, we wanted to figure out the derivative of the inverse at this particular point. Here's where this gets tricky. This point is on the original graph. So if I took the x value of 1, cube it, add a 1, I would get a y value of 2. So it's on this point. This point is not on the inverse. If this point is on the original function, then what we know is on this function, the inverse is the point 2, 1. So when I now go and evaluate this, we need to plug in an x-coordinate. We don't want to use that original x-coordinate because that's x on the original function. The x-coordinate on the inverse would actually be the y-coordinate of the given point. So that's why up here it says you want the derivative of the inverse at your y. So the x value we are picking is not 1, but the flipped point, which is 2. So if we let x be a 2 here, you'll get 1/3. And then if I just plug in a 2 for x, I'm going to do 2 minus 1, which is 1. 1 squared is 1. The cubed root of 1 is 1. All that gives us a 1, so our answer would be 1/3. That's our answer. Okay? That's sort of the hard way. This is our preferred way, using the reciprocal. And this is the way that we did a lot of them. You're going to take your derivative normally, so 3x squared. All right, nothing much easier than that. What we can do to find the derivative of the inverse is use the reciprocal. What that means is I'm going to now find the derivative of the inverse by simply taking the reciprocal of this. We need an x value to plug in. Notice how here we actually found the inverse. That's why we couldn't use this point. Here we never did. We found our original derivative and we did the reciprocal. That means you can just use your original point and not have to flip-flop your x and your y and just let x be a 1. And then just like we did with that other method, you're going to get a 1/3. Okay, 1/3, 1/3. So ideally, your best bet is to just take the original derivative, flip it, do the reciprocal of it, because once we do our reciprocal, that magically turns it into the inverse. Then, a problem. This is on the test that I gave you. It's a release test here. Is dealing with this idea. Let f be a function defined by this. So this is our function. The inverse of f, so f to a negative 1 here, so the inverse of f is defined as g. So this is our original function, this is the inverse, g is the inverse. Then they tell you on the graph of g, we have the point 2, 1. Well, if g is the inverse, the point 2, 1 isn't on this graph. The point 2, 1 is on this graph, the point 1, 2 is what point would be on our original graph. Question is then asking, what is the value of g primed of 2? So over here, to take the derivative of g is equivalent to taking the derivative of your inverse. So the derivative of an inverse is what we're doing up here. We would like to do this, to use your reciprocal. So you're going to go to the original function, take its derivative. So f primed of x equals 3x squared plus 1. If we simply, let's get rid of that for right now. If we just write the reciprocal of this, 1 over 3x squared plus a 1, that magically then becomes the derivative of the inverse. An original derivative and its reciprocal are always the inverse's derivative. So that's our inverse derivative. here's where this one gets tricky. The x-coordinate that they gave you was the x-coordinate on the graph of g. We are dealing with the original function, and the x-coordinate for that function at this point would have been a 1. So you take your 1, plug that in, and you will get 1/4. All right, which is B. All right. Okay, that's pretty much it. If any of this is still confusing to you, see me. I can try to do a little bit better explanation of it, give you some more examples, but that's pretty much it. You will see a question probably on the asymptotes in some capacity. May or may not see the exponential growth and decay, and you will almost certainly see a question on the inverse derivative. All right, I think that is it. See me if you have any questions. All right, guys, talk to you later. Bye.